Welcome to Innovation Design Engineering, our workspace at the Royal College of Art and Imperial College London. And these are my colleagues Rodrigo,
hello,
King,
hello,
and I'm Paul.
For the last 2 months, we were working on an experimental project called formo. We were investigating the ability of objects to change shape.
So, we would like to invite you on a journey through the world of our project.
As designers, we asked ourselves the question, what should form follow? Form is the shape and structure of an object. Some people say that form should follow function, and others say emotion, or context, or efficiency. There are many different shapes for many different reasons, and many of these shapes never change during the lifetime. Design faces wicked problems. There is no perfect form because the requirements are changing. So form should follow function, context, user, and many other things. These variables change over time. So what if form could change as well and truly follow them? What would this material or structure look like? And how would it work?
To find mechanisms for shape change, we explored responsive and so-called smart materials that change due to different triggers. We worked with materials including muscle wire, paraffin wax and ferrofluid and examined how non-Newtonian fluids work, how an electromagnet can modify the shape of metal dust, how hydrogel expands rapidly and how a resin grows when it has contact with the catalyst. We recorded all of our experiments in a recipe book and created a project map to be able to establish connections between them and draw conclusions. Our main inspiration, though, was nature and the way organisms can change and adapt in response to their environment, even during their lifetime. This change is called phenotypic plasticity and is a result of changes on a very basic level, the cells. Inside, cells have a cytoskeleton which provides it with structure and shape and works with the principles of tensegrity. With only a few parts in compression inside a net of continuous tension, these structures are highly efficient. We were stunned by the beauty and elegance of this movement and want to translate it into the world of man-made objects. So we considered the following question: what would be the basic unit, the cell, of a shape-changing structure?
Using fabric in tension and wooden sticks in compression, we were able to create collapsible self-supporting structures. At the same time, we explored different scales and miniaturized tensegrity structures, using a 3D printer to apply a pattern of compression parts to a pre-stressed fabric. Using a closed hydraulic system, we were able to change the shape of a unit just by redistributing the amount of water in each compression part. In every configuration, the strings are in tension and the unit, as a whole, is stable. Adding more units resulted in an intriguing movement.
After exploring the possibilities of shape change for one unit, we investigated how an assembly of several of these units could change. Changing the size of circles in a system alters the curvature of the surface. For this, we considered different actuation methods. We used a motor to increase or decrease the diameter of the circle. Another way was linear action and a scissor system. Response to temperature could be achieved with paraffin wax in a piston that expands when heated. A combination of the principles of tensegrity and the visually pleasing assembly of circles led to our final design.
By transferring the length of the base to the top, different curvatures can be achieved. Combining these units allows a more versatile shape change. In 3 dimensions, the unit is a combination of 2 basic tensegrity structures. In this way, we achieve lightness and in the same time good structural properties. Several units form a hexagon, and many of these hexagons form a planar structure, like a surface. Thanks to the properties of the unit, the shape of the surface can be manipulated in 3 dimensions without compromising the structural properties.
In this design, the joints are the main functional elements, and so we experimented with different variations. We designed and prototyped ball joints to allow the parts to move. Casting flexible hinges from rubber allowed them to accommodate the rigid parts. This led to a smaller number of pieces, for which high precision manufacturing was required. We used the CAD software Grasshopper to rationalize the geometry of the surface. In this way, we were able to explore its abilities with different patterns of actuation. We actuated a real scale prototype in different ways. Several stages of modification and improvement led to the design of our final experiment.
Our vision is that formo can be applied to many different scales. For example, as the material of car interiors, formo could provide flexibility to different uses. Used in car exteriors, the car can change its shape for better aerodynamics. In a bigger scale, formo can be applied to infrastructure or buildings. And it can improve the performance of wind turbines and wings of planes. As formo has the potential to be miniaturized, we see it as a new communication tool between the physical and digital world. Formo, a configuration of matter that enables objects to change shape.